So my name is Simon, and I'm from the Energy. To call it the Energy for Informatics Center at SDU, and we're gonna discuss our research paper, a software research paper called a QR code-based framework for auto configuration of IoT sensor networks in buildings. So the whole purpose of this paper is an exploration of how we can utilize QR codes to deploy, configure, and maintain IoT devices with minimal human interaction. And the reason for this is because at the moment IoT networks in buildings are very expensive and usually only fitted into new buildings. And installation of a new IoT environment it requires a lot of manual work and becomes very labor intensive when you have over 1,000 devices you have to configure. And also with the many different vendors, there are many implementations that also adds to the complexity of how an autonomous system should orchestrate different IoT configurations. And the proposal we are giving is that we would like to give a cost-effective energy management system that can be deployed in both new constructions and existing buildings. So therefore, in order to increase the flexibility of the installation process, we propose the use of QR codes to register components in our system. So QR code solution is an integral part of how we can manage the amount of labor required for the registration process. We provide a QR code extraction for physical contexts, and manufacturers provide the QR codes for their own devices. So we can associate these QR codes by utilizing a mobile app as the deployment entry point, and then we can use a middleware to configure and monitor the devices. So it really boils down to QR codes being available at the installation location, and then scanning the QR codes of the wanted IoT device, and then sending this data somewhere to some middleware that executes this association. So in order to streamline the deployment process of IoT devices in buildings. So we're going to talk a bit about how we do that. So this is the architecture of our system. So if we start from the bottom, we have our IoT devices. So we have sensors that collects the telemetry, and we have gateways that serves as a communication hub for the paired sensors, and they are centralized elements with a small, powerful processing capacity. And to read the data from the devices, we utilize a broker, a MQTT broker, or a UPC-UA server to collect the data that the sensors have collected. And we all do this in a big backend that is also the so-called middleware that collects everything and orchestrates every configuration and communicates with every applications that we've built. So we've built a mobile app in order to deploy our IoT devices, and we've developed a web interface in order to monitor our devices, and we have a database just for storing. So QR codes. So how can they be useful? So usually you've probably interacted with QR codes in many ways on consumer products, but usually they're static because once they're printed, you cannot change them. So in order to really leverage the power to maximize the power of our QR codes, we embed them with a identifier that on our middleware that can be identified as a unique element. So instead of having a static object here and just embedding our building data directly into the QR code, we have an identifier instead here on the second one that just facilitates a web request, and then we have a flexible object that we can change if we want to, because we cannot change the static QR codes. So we do this by using a mobile app that scans the QR codes. So on the right, we have a very simple UI interface where you can scan your IoT device and the location, and then register the device by swiping up to the right, and then the configuration happens in the middleware. And when I say configuration, I really mean that some pairing strategy is going to be applied, which means the way that our middleware is going to pair the specific sensor to a specific gateway in our building. So in the paper, we explore a couple of different strategies. So we have round robin, for example, which is just a brute force method, which checks the individual signal strength one by one and after the last gateway in the building has been tried, the sensor pairs with the most stable one. So this strategy is a very slow one, but pairings usually last for a long time. So maybe that's not an issue. We also have some more intelligent strategies, such as a physical constraint strategy, which is where you limit a gateway to only be able to pair in certain within certain distance. So we have I think we have an example here of the round robin function. So we essentially just try all the gateways in our network, and then we try to pair it with the sensor we are trying to deploy in the network. And we're just going to check if the signal strength is better than the last gateway that we tried. And in the end, we're going to just pair it to the one we found the best. So more strategies are discussed in paper, and in general, the more complex and intelligent of a strategy you make, the more preparation a strategy takes. So go back to the physical constraint strategy. It takes a lot of physical planning to constrain the gateway to some specific locations. So we've also, in order to maintain our system, we have created a simple web interface that its purpose is a graph view to reflect the current layout of the whole network and the connection between them, what floor they're on, what building they're in, what room they're in. So we see we have a tech building here on floor 2, and in the room Jarvis, we have a disconnected sensor, the red dot here, and we have green ones. And the arrows indicates whether or not they are paired to some specific gateway. So the graph view also supports replayability, which is the most important part, which means in the top play bar here, you can drag it across to see the configuration changes over time. So example of network changes could be that a device has changed location, or online status has been changed, or a device has changed pairing, and so forth. So replayability allows the user of a monitoring web interface to learn about the network's behavior over time. And if necessary, you could react proactively to mitigate issues that might arise. So for example, if you consistently see some sensor in a room that hasn't been paired, there may be something wrong, and so you have to investigate. Whoops. So whenever we interact with one of the nodes in the graph, we just get a normal data graph view of our sensor, what it has, what telemetry it has collected. So here we have a temperature sensor that actually also collects illuminance, so we can measure that. So we tested our whole system at the mask building at our university, and some of the sensors that we installed in the building are here. So we have motion sensors, window sensors, and door sensors installed in various locations, as you can see here. So we have 4 different rooms with 4 gateways and sensors in the individual rooms. So because of COVID-19, we had to orchestrate our system test remotely, which means that we cannot interact with the sensors physically, which is of course annoying, but we have to deal with it. So in our setup here, the system has a default pairing method of a round robin. So every time a new sensor is deployed, it tries to connect to each gateway, even though there's concrete walls between the gateways and the rooms. It even tries those. So yeah. So what we did here was we tried to disconnect a gateway and see how the system would react to it. So whenever the system registers that a component has been disconnected, it tries to heal itself. So we try to disconnect the gateway in room 2. So by removing it, the sensors has to find a new gateway to connect to. And what we see is we actually have we almost connected every single sensor back to a gateway in order to not lose any collection of data. And this was over. So pairing can usually take between 15 minutes to an hour because of the wide distance between the gateway and the sensors. So over the course of an hour, we could see that five sensors had restored to working, and a single sensor couldn't be restored because of it had too great distance to reconnect. So just to summarize it all, Yes, we've streamlined the deployment of IoT devices with the use of a very cost-effective method of QR codes, which enables to quickly associate devices to a physical context, and then we provide this data to a middleware to automate the pairing process, the configuration process, and then we use the web interface for maintaining the whole sensor network. And future work is that we are trying to utilize. So this was a very, very small setup. So in the future, we would like to try a much. We have testing facilities in other parts of Denmark that we're going to try later. So yeah, I think that's it. So we can take some questions.